Okay, today should be the final day of microscopic muscle anatomy and the physiology behind how a muscle contracts. So far in class, we have done this part. We have done a neuromuscular junction, how a neuron interacts with a muscle fiber and basically tells it what to do. We have also done this, how a muscle actually contracts, calcium, cross-bridge cycle, sarcoplasmic reticulum. What we need to cover today is how these two connect with each other. An example I gave earlier is on one side of the room, I have Chris. On the other side of the room, I have Sloan. Chris is thinking to himself, I really like to talk to Sloan. She's a good kid. He can't get to her. She's so far away. How can he communicate? That there's a big gap between these two kids. There's a big gap between the neuromuscular junction and the sarcoplasmic reticulum. How do we get them to communicate? That's the goal for today, communication. So the way that this is actually done is something called an action potential. And that is what today's topic will be all about. An action potential is basically a little zap. It's a little zap that sends a signal across a cell so that a specific area of cell can be activated. I likely will have to switch my camera on because there's some things I really want you guys to see and I want to get it on video. But to define an action potential is a change in a change in polarity between the inside of a cell. For those of you that have been in my classes, what do we call that general area inside of a cell? Cytoplasm. And the outside of a cell. Can anyone recall what the outside of a cell is called? Extracellular space. I love it. Just like the area of space beyond the Earth is called extraterrestrial space, the area of space beyond a cell is called extracellular space. So I am going to turn on my camera here for a second because I want you guys to see something very clearly. So give me a moment to set that up. This is the way I want to do it. Okay. Let's see if I can make this bigger. Watching at home, just give me a second to get this worked out. Okay, I guess I'll figure it out. All right, where's Jack? There he is. Jack, you're gonna help me out with this. You're famous. Wave to the people. All right, Jack, you and I are gonna demonstrate how action potential actually works. So I want you to take this ball of yarn and let's just kind of stretch it out a little bit. All right, now, I need one end. Focus on this. Just worry about this straight. There we go. Just perfect. All right. Now, Jack is going to be the end of a neuron. I am going to be the beginning of a neuron. The signal goes from me to him. It's like I'm the dendrites, he's the axon terminal. This whole thing is the axon. And the way a signal actually travels is kind of like this. Takes me a few tries to make it right. There we go. You see how it's traveling down? Trying to get this perfect. Jack, pull a little tighter. There we go. There. It travels down the axon. Notice that as soon as it goes, oh, keep pulling. Notice that as soon as it travels down, this little part is up, and then everything behind it goes back down again. When a neuron is like this, It's at a resting potential. It's negative on the inside, positive on the outside. But for a split second, literally like a fraction of a second, the polarity totally flips. And instead of being negative on the inside of the cell and positive on the outside, it's positive on the inside and negative on the outside. And it makes that little kind of kick action. You can do this with a dog's leash, or you do it with a hose in the backyard. It's the signal traveling down the actual neuron. Well, what we're going to do, you can let go, is how this actually travels down a muscle fiber. Okay. Don't worry about it. I'll clean up later. Okay, and we're back. So, screen fixed. There we go. All right. So normally, a cell is at resting potential. When you guys are unstimulated, and when I say unstimulated, I mean there is no stimulus. There's nothing to smell. There's nothing to see. There's nothing to taste. There's nothing to hear. There's nothing that touches you. You're unstimulated. You are at resting potential. And then suddenly when you're taking a test, I go, guys! And some of you go, ah! You're not in resting potential anymore. That's an action potential. It's very brief, but very direct. At resting potential, the cytoplasm has an overall negative charge . And the ECS, from here on out, I'm going to call the extracellular space the ECS, just to save a few seconds of time. The ECS has an overall positive charge. So the way that we look at this, guys, is if this right here is the sarcolemma. And for those of you that have been keeping up with this stuff, what is the sarcolemma? If you said it is the plasma membrane of the cell, you are correct. What kind of cell? A muscle fiber. Good. Normally, guys, at resting potential, here's how it looks. The outside is positive charges, and the inside has negative charges. That's at rest. I would assume that most of your muscles are like this right now, because right now you're not really using most of your muscles. You're using your muscle in your arm to write, and you're using the muscles in your back to sit up. That's about it. But then at an action potential, we're going to call that an AP. It is completely flipped. But this is where it's very tricky to draw. It might be even trickier to try to understand it. I'm going to do my best to get you guys to really understand this. Watch this. Where's the action potential on that one? Do you see it? Isabella, you are an AP Bio. Where is the action potential here?
On both sides.
But where on this image? Where do you see it?
Inside and the outside.
An action potential is when the inside is positively charged. That's it. So where on this cell is it positively charged?
The inside.
Is this the action potential?
No.
Why not? Okay, because it's negatively charged on the inside. Is this the action potential? Yes. That is the action potential right there. The action potential is in that spot. And what if I told you the action potential is moving from left to right? So Sloan, has the action potential already been here?
Yes.
Yes. I want you guys to notice something. Whenever the action potential is traveling down a muscle fiber, any place that it is not currently located is at resting potential. It is negatively charged. Something I did last period, and it kind of helped the kids. Check this out. If you're listening to the video, I'll try to talk you through it. Right now, I'm standing in front of no one. I am going to make your life positive when I am in front of you. When I am not in front of you, your life is negative. So right now, I'm in front of Grace. Grace, how you feeling? Give me a high five. You feeling positive?
Yeah.
Perfect. How about now? Why? I'm gone. It's Scout's turn. You feeling good, Scout? Great. I'm going to move away from you. How do you feel now, Scout?
Negative.
So this area was positive, but the action potential is moving forward. How you feeling, Eva?
Great.
Great. You feel positive?
Yeah.
How about now? Nope, I'm gone. As soon as the action potential moves on, she was negative. Then when I was there, she was positive. And then when the action potential leaves, she's back to negative again. The action potential is a temporary change in the polarity of the membrane as it travels down the cell. So when you look at this diagram, that area that I have highlighted in a green circle, that is where the action potential is. Notice that everywhere behind it went back to resting. And everywhere in front of it where it hasn't been yet is also at rest. The action potential is, it's, I don't know if I can describe it any other way. I'm going to shoot a fireball at Tyler. I'm going to blast you with a fireball. Now, everywhere behind the fireball is no longer there anymore. It's gone. Everywhere in front of the fireball hasn't had it yet. It's just where the fireball is. That is the action potential. It's like a little lightning bolt that travels down, or like a little bullet that travels down. So there are several stages of an action potential, and we measure it on an XY axis. The x-axis almost always is time, and it is going to be measured in milliseconds, like a tenth of a second. So we have 1, 2, 3, 4. And the y-axis is millivoltage. We start off with negative 70 millivolts, negative 55, 0, positive 40. And the diagram looks like this. Did they teach this to you in psych? They do? Some people last period said yes, some people said no. This is what an action potential actually looks like. Actually, I made that a little too high. Let me fix the number here, positive 40. The peak is at about positive 40 millivolts. What we're going to do is we're going to describe the various parts of this graph and explain what's actually happening. And this should fill that gap between the neuromuscular junction and the sarcoplasmic reticulum, how the two connect with each other. So the first one I'm going to do is this flat line at negative 70 millivolts. This is going to be number 1, step 1, resting potential. Unless you are stimulated, your muscles are at resting potential. Okay. At resting potential. The polarity inside the muscle fiber is positively charged. And the polarity of the muscle fiber the polarity of the, not the muscle fiber, the extracellular space is, did I do this right? I am such a doofus. What did I write incorrectly here? What is wrong with what I just wrote? It should be the polarity outside. So rather than erase everything, just cross out inside, scribble, and replace it with outside. At resting potential, the polarity outside the muscle fiber is positively charged, and the polarity of the cytoplasm is negatively charged. Sorry about that. So it's negative on the inside, positive on the outside. But there's more here to unpack. The majority of the cytoplasm is K. What element is K? Potassium. The majority of the ECS is Na. What is Na? Sodium. So you have a lot of sodium outside the cell. You have a lot of potassium inside the cell. Now, I just want to draw something for you guys, and I want to answer a question that I've gotten every period today. You do not have to draw this. I just want you to see it. You don't have to draw anything. This is the sarcolemma. And outside, you have sodium, 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 sodium. You have a little bit of potassium. I'll throw in a couple here. But that's how it typically looks outside. Inside, you have potassium, 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 and you have a little bit of sodium sprinkled in there. Now, the question I'm beginning is, Mr. Thorson, how can the inside be negatively charged if all those ions are positively charged? I never took chemistry, but I know a positive symbol when I see it. That's a great question. Why is the inside negatively charged when all that stuff is positive? The answer is because the organelles, the ER, the Golgi, all that stuff, and the cytoplasm itself has a negative charge. And it overwhelms these positively charged ions. So despite the fact that all those positively charged ions are inside the cell, the inside of the cell is still negatively charged because the overall cytoplasm and all the organelles have a negative charge. And that's more than these can overcome. Okay. So just in case you were wondering, that's why. All right. So this is how things are at rest. The next thing we're going to do is when things start to get a little exciting. This is called depolarization. That entire incline is called depolarization. Okay, so a depolarization. The polarity between the cytoplasm and ECS is flipping. The inside is becoming more positive, the outside is becoming more negative. Here's what's actually happening, everyone. Acetylcholine from the neuron opens ion-gated channels along the sarcolemma. What is the sarcolemma? The plasma membrane of a muscle fiber. What is ACH? Acetylcholine. Okay, so here's how it looks. Here's the channel when it's closed. This is a closed ion channel. And then here's an open ion channel. Those little red things on top of the channel, that's ACH. ACH is basically the key. Without acetylcholine, you can't open those channels. Now, in this idea, sodium is rushing in, and potassium is rushing out. Sodium rushes into the cell, potassium rushes out of the cell. And this is the last part I'm going to add. More sodium enters than potassium exits. The polarity of the inside of the membrane is changing. It's becoming more positive. This is depolarization. Whenever you begin the word with DE, you're going to undo whatever the root word is. So if it's polarized, you're going to depolarize it. If you're ascending, you're going to descend. If I'm inclined to agree with Isabel, the opposite is I am declined to agree with Isabel. So whenever you put DE in front of the word, you do the opposite of whatever that word means. So if something's polarized, you're going to depolarize it. You're going to do the opposite. Now, guys, you don't need to draw this, but I just want to visualize this for you. As you go up, the inside is getting more and more positive. Look at that. It gets more and more and more positive. But there is a certain point of no return, and we call that the threshold. Last week in my AP biology classes, my students signed up for the AP biology exam. When they sign up for that exam, there's no turning back. You're in it for keeps. The dropout date has come and gone. So that is the threshold. That's the point of no return. When you cross the -55 voltage barrier, you have committed to this whole process. You have committed to the action potential. Once you cross that line, more and more and more of these sodium ion and potassium ion channels open, which causes more sodium to come in and more potassium to go out. And this continues to make the insides more and more and more positive until you reach the tippy top right here. This is going to be part 3 in action potential. The screen will come back on. I wrote action potential for number 3. That's all I've done. There we go. It's the very top of the peak. That's it. Okay. This is the most positive the inside of the cell can achieve. It is a positive 40 millivoltage. This is what actually is going to be carried down. This is like the bullet. This is the bullet that is traveling down the cell. Now, a bullet cannot be everywhere at once. A bullet is in one spot in time. If a bullet was shot across this room, and if the bullet is right here, this pen of mine is the bullet. Everywhere the bullet has been is in the past. The bullet's not there anymore. Everywhere in the front of the bullet that the bullet hasn't been is the future. It hasn't been there yet. The action potential is very similar to a bullet. It is just traveling down the entire cell from one area to the next, point A to point B. Once that action potential has reached its peak, the area of the neuron that it was at needs to return to its normal polarization. So that's going to be our fourth step. This is going to be depolarization. You're returning back, or excuse me, not D, repolarization. Whenever you put RE in front of a word, you're going to kind of do what you did originally. I'm going to redo my work. I need to reread that paragraph. I need to return my library book. So number 4 is going to be an action, or excuse me, a repolarization. If you're curious, there's a total of 5 steps. We're almost there. Okay, in this stage, the cell is returning to the resting potential state. Sodium ion channels open throughout. What I do? Oh, I meant, yeah, okay. I didn't mean to say, I meant to say potassium. It is potassium. Potassium channels open throughout the sarcolemma. Potassium ions exit the cell. Sodium ions remain in the cell. The millivoltage of the cell declines or decreases. It's getting more negative. Okay. At the end of repolarization, conditions are opposite of RP, resting potential. When we had resting potential, sodium was mostly on the outside, potassium was mostly on the inside. You have the exact opposite of that now. The ECS is mostly potassium. The cytoplasm is mostly sodium. If you're wondering why sodium and potassium, these things are called electrolytes. When you don't have enough electrolytes in your body, you get cramps. A cramp is when your brain cannot tell your muscles what to do when you want them to do it. It's an involuntary muscle contraction. When a girl says, I have cramps, that's her smooth muscle. But the point is she cannot control it. When you get a cramp in your calf, you get a cramp in your abs, you get a cramp in your arm, you can't control it. That's what happens when you have an electrolyte deficiency. If you watch the football season, In September, when it's still really hot out, there are players dropping left and right because they have muscle cramps. They basically need to be given a bunch of salt water. And that's what Gatorade really is. That's why so many sidelines in sports, no matter what the sport is, they have Gatorade because it returns those electrolytes to your system. Tyler, when you're running on Bayshore, do you drink any Gatorade when you're done?
I do on some, like after meets and after really long.
Because you're sweating a lot, right? What's in your sweat?
Salt.
That's what electrolytes are. Potassium is a salt, sodium is a salt, magnesium is a salt, calcium is a salt. Those are all electrolytes. You're sweating those out. The more electrolytes you lose, the less you still have in your system, the more likely it is that your brain cannot effectively communicate with your muscles. So these things, sodium, potassium, calcium, they are electrolytes. It's how your nervous system instructs your muscular system. When you run out of it, it's kind of haywire and it doesn't work right. Back when your grandparents were around, maybe your parents, I doubt it, your grandparents probably, they would have a salt tablet. Their coach would give them a little disc and it was salt. And you just put it on your tongue and let it dissolve. That's how they did it back before Gatorade and IVs and all that stuff. Like, coach, I have a cramp. Take a salt tablet. When I was in high school, we always had a bunch of bananas on the sideline during practice, just because bananas are a huge source of electrolytes. Okay. So if you guys look over here, I want you to see that the majority of the cytoplasm is potassium. And the majority of the extracellular space is magnesium. Now look at what we have here. We have the exact opposite. We have to flip it. And so this is the fifth and final step. The fifth and final step is going to be hyperpolarization. Here we're going to have the sodium-potassium pump. The sodium-potassium pump is an active transport process. So because it is active transport, what does it require in order to work? It needs ATP. I don't know why my computer keeps blacking out like that, guys. I'll say what I write. It needs ATP. This is ridiculous. Come on. This pump is going to pump 3 sodiums out at a time. It's going to pump 2 potassiums in at a time. So here's the pump. These guys go out. These guys go in. 3-to-2 ratio. 3 sodiums exit, 2 potassiums enter. This returns the cell to a resting potential. And you're right back where you started, and the cycle is complete. Everything is where it should be. So here's how I think this is going to have to work. There's a lot of details here. It's not hard. It's just a lot of details. It's going to take a while, I would say a day, to let your brains really take this in. So when you come in tomorrow, I'm going to have an assignment for you where I'm going to have everything that we've described here, but it's going to be all scrambled up. And you are going to put it in order, in the proper sequence. It's like if I gave you your schedule for your daily class routine at school, and I just cut your schedule up into pieces and I have all the classes scrambled up, you need to put them in the right order. That's what we're going to do with this. Okay? So that will be tomorrow.